Topic of this lecture is determination of thickness of mica sheet and unit is interference. I am using here supporting physical concepts, and with the help of that I will try to explain this particular topic. The first supporting physical concept is Young's double slit experiment, which I have already discussed in last video. Second point that I am saying is the supporting physical concept is constructive and destructive interference condition for path difference, that basic information. And at the number 3 and important, and the first part of this topic is speed of light in air or vacuum and in any medium, that is the transparent medium, have refractive index mu. So these are three supporting physical concept. With the help of that one can understand this particular topic. Right, myself here Sushil Kumar, and if you want to know more about such lectures, then you can visit www.apniphysics.com. So the title of this topic is Displacement of Fringes, or you can say determination of thickness of mica sheet. So both the concept basically we include here in this video lecture. If you have to find out that how much displace the fringes, or you have to find out the thickness of mica sheet, then you can watch this video lecture. The first concept, you know that is speed of light c in air. Right, we represent it with the symbol c, and the speed of light in any medium that's have refractive index mu, we denote that by v. This ratio of the light in vacuum or in air with the medium, that is v, is equal to the mu. So if you have to define the refractive index, you can use this ratio. And if on the other hand you have to find out the velocity of light in any medium, then you can use this formula c upon mu, where c is the speed of light, that is 3 into 10 raised power 8 meter per second, and mu is the refractive index of the medium. Here the point is that mu, which we have considered, is medium. That medium is transparent. So v is the speed of light in any medium, and v will be less than as compared to the c, that is the speed of light for any medium. It means longer duration to cover the same distance. Right, this is c speed of light, you are dividing it with the mu. Mu may be of water, mu may be of glass or mica sheet, whatever. So obvious, this is first point of this topic. Now actually what happens when we inserted a mica sheet in the path of a light ray? Let's begin. So when a mica sheet of refractive index mu and thickness t is placed in the path of one of the two sources, then the center of fringe is shifted to a new position. What is it means? Here what we did, there are two sources S1 and S2, as you have seen into the Young's double slit experiment. These two light ray basically approach to this point, or you can say that joins at this point P, and either here a constructive interference pattern will develop or destructive interference pattern, but it depends on the path difference, right? That conditions. What we are doing, we have here two sources S1 and S2, as I told you, and we have just put this mica sheet of thickness t, refractive index mu, in one of the light ray path S1p. In the path of S1p we placed this mica sheet, right? So now we are saying that when we put this mica sheet in the path of light ray, the center of the fringes without the mica sheet was O. Now it has been shifted to the O prime. This is the idea. Right, I am repeating again that basically this is the concept, this is the idea of this topic. When you place a mica sheet in the path of a light ray out of the two, then what happens is center of the fringe is shifted from O to O prime. How much it shifts, that distance we have to find, right? And the fringe width and the comparison without the mica sheet, these things we will see. So now the explanation. Suppose mica sheet is in the path S1P. As I told you that velocity of light in air and mica medium is different. So this light ray right now here is in air and it enters into the mica sheet. That thickness is T. So now light ray is traveling through the mica sheet and then after it comes into the air. This is the point, and velocity of light will be different as I told you earlier in air and in medium. So the path difference change and hence central spot shifts from O to the new position O prime. So for this purpose, first of all what we are doing, we are drawing a perpendicular S1C on S2P. As you can see here, we draw a perpendicular from the source S1 on S2P. So this is the perpendicular S1C, and here theta, if I join this S1 point, now I am joining this S2 point and this F point. This is the distance between the source and the screen, and this distance we represent with the capital letter D. The distance between the source S1 and S2, this distance is denoted by a small d. One can write here and you can see it in next slide also. So this distance is small d is in between the source S1 and S2. This angle theta is this one P, S2 and F triangle. So this is the angle theta, and by the property this one C S1 S2 angle will be theta. So here these are the basic explanation of this diagram which we have used earlier also. So now we will use some geometry. You have seen here that this is the source S1, this is the source S2, angle theta, theta, this one, perpendicular S1C, mica sheet of thickness T, refractive index mu, and the distance between the two sources. O is the origin without the central point of the fringes without the mica sheet. This distance is x with respect to this origin O. So now we are using the first triangle S1 C S2, S1 this C and S2. So this one is the angle theta, so sin theta will be equal to S2C upon S1 S2. S2C is this, that is the perpendicular, and divided by S1 S2, this one. This is the base, S1C is the base. So this will be equal to S2C upon D, where S1 S2 is equal to, as you know, that is the D, small d, and from the S2PF, this S2, this S2, this P and F, bigger one. In this triangle, this angle is the theta, so sin theta will be equal to this PF and S2P. So you can see here, this is the PF divided by S2P, and by using the triangles property, so this will be same. So we are putting S2C upon D equivalent to this ratio. So S2C upon D is almost equal to the PO upon D. So we can say that these are almost equal. So we are putting PO instead of PF, and S2P, that distance you know is capital D. So putting this value and rearranging the term, we are finding out here the distance S2C, that is basically the difference between the two light rays. So equal to PO dot D upon capital D. If PO is denoted by small x, then it will be equal to S2C will be equal to X dot D upon capital D. This is equation number 1. So first of all, what we just try to find out this distance S2C, and this distance basically is the difference between the two light ray path, right? From the C and from the S1, light starts to travel and reach at the same time here at the point P and get interfere. So now the path difference is equal to S2P minus S1P for light, as we have calculated earlier in case of simply without the mica sheet. The path difference S2P minus S1P, but here we have to define this S1P also. What is this S1P? S1P is this one, right? And you know that light travels here through the air and mica sheet. So we have to find out the total path traveled by the light ray, that is first of all in air, will be equal to S1P minus T. If you subtract the thickness of the mica sheet from the total distance, that will be the distance by which light ray travel into the air, and second distance is that mica sheet, right? And then the total path traveled by the light ray will be mu into T. So by this way, the light ray traveled by the total path will be S1P minus T into air and mu T into the mica. Now we have to put this value S1P here to find out the path difference, and now the result is S2P minus this S1P minus T plus mu T, and now we have to simplify it. I hope I have made it clear that why I am writing S1P in this way. So after simplification of this equation, when you simplify it, S2P minus S1P plus T minus mu T. Now after simplification of it, as you know that S2P is equal to S2C plus CP. S2P is the light path from source S to that point P, right? So here S2C is that distance. This C was the perpendicular, S1C was the perpendicular, this was the C point, this was the S2, and here was the P point. If you remember the last picture, so you can write S2P is equal to S2C plus CP, and CP is equal to S1P because the path is same traveled by the light ray. So you can see here this S2C plus CP is the S2P. So if I have to write S2P, so I can use the sum of S2C plus CP. The second point, S1P is equal to the CP, right? This is the equal, S1P is equal to the CP, this distance. So now so you can see here that CP we have so you can see here that CP is equal to S1P, the distance is equal. So putting this value here of S2P, that is equal to S2C plus CP, and as it is these three terms S1P, T and mu T. Now CP is equal to S1P, so this is minus, this one is positive, cancel out, right? These two terms cancel out and you are getting S2C plus T minus mu T. And now rearranging the term, we are getting this delta X, that path difference is equal to S2C minus. So this is the path difference. And now when you place the mica sheet, then the center point of the fringes will shift from O to O prime, as I told you earlier. And now this path difference will satisfy the condition for the maxima, that is n lambda. Delta x should be equal to n lambda if the central spot of the fringes is bright. Now this is the form xd minus xd upon capital D minus mu minus 1t is equal to n lambda. Now simplifying this equation, put this mu minus 1t with the n lambda, this becomes xd upon capital D is equal to n lambda plus mu minus 1t, and for the x this is equal to d capital D upon small d and this factor n lambda plus mu minus 1t. Here x basically is the distance of the point P at which nth bright fringe will form when mica sheet is placed in the path. If there is no mica sheet, then that means t is equal to 0. If I put here t is equal to 0, this factor becomes 0 and we get xn is equal to d capital D small n lambda upon d, and this result is almost same as you have seen into the Young's double experiment without the mica sheet. For n is equal to 0 in mica sheet case, from equation number 4 watching upside, this one xn, for n is equal to 0, then x0 will be equal to mu minus 1 dt upon small d. And you know that what is the x0? x0 is the point basically when n is equal to 0, the 0th order of the fringes, that means the central point. And if you see here, in case of Young's double slit experiment, this is the result, xn is equal to d n lambda upon small d. If I put here n is equal to 0, x0 becomes 0. That means it is on the center point, that is the O, right? It means that. But here when we put n is equal to 0, we observe some positive value of the x naught, and that is mu minus 1 capital D small t upon small d. And this positive value of x naught indicate that our center point of the fringes has been shifted to the upward. Why upward? Because x naught is positive. Mu is greater than 1. Mu is equal to 1 for the air. Rest of the medium it will be greater than the 1. Right. So mu is greater than 1, and because of that x naught will be positive. If x naught is positive, it means it is just above the 0. It means the picture which you have seen earlier is in favor of this statement. As you can see here that this is the center point O, as without the mica sheet, but when you place the mica sheet, this O shifted to the upwards, and now this is the knee point. At this knee point, right, is x naught. The distance from O to O prime, that distance is x naught, right? So O prime is the knee position of the bright. So now you can see from here, as I told you, that x naught is the distance from the earlier position of the center point, and that is mu minus 1 capital D small t upon small d. Right, I am sure that now this idea is clear. When we place the mica sheet, our central spot basically shifted to the upward direction. So x naught in mica sheet case is just above from the earlier center O, and new position is O prime. So you can also determine the shift of center, that how much it is shifted, that you can determine with the help of O prime. That means the distance, if you have to calculate x naught in case of when you place mica and x naught when there is no mica, so the difference between them is equal to capital D upon small d mu minus 1 into the t. Right, so this much is the amount by which the new position you get. So next point, now the fringe width that can be calculated by the separation of two consecutive fringes of the same kind, whether that is the bright or whether that is the dark. So the separation of the two consecutive fringes of the same kind, and here we are taking the bright fringes. So beta is that the fringe width and is equal to xn minus 1. Beta is capital D lambda upon small d, and that is the constant, and small d, that is the separation between the two sources, as you have seen into the Young's double slit experiment of mica sheet here, and the refractive index. So it is independent from the mica sheet. So here further we are simplifying it, that this ratio capital D upon small d here is equal to beta upon lambda, as x naught is equal to, you have seen, capital D upon d mu minus 1 t. So this can be written as in terms of beta upon lambda also. So I am putting that value capital D upon small d from the last slide here. You can understand that the summary of this lecture is, when you place any mica sheet or any transparent medium into the path of one light ray, then the central maxima, basically the center point of the fringes, shifts only. There is no other change we observed, right? So there is no change into the fringe width. The change comes only into the shifting of the central point, right? And that distance is x naught.